Co-17C. Today is March, what, 6th?
Yeah.
Yeah, it's literally right in front of me. Just okay. More probability. Probability. Section 12.2. Let's look at this first example. A fair coin is flipped 4 times. Or alternatively, you can think of it as 4 different fair coins being flipped all at the same time. I kind of like that. I thought of it just because that way I can kind of think of one coin being painted red, blue, green, and orange so that they're distinguishable from each other. Either way, we're going to start off by listing the sample space. So depending on what you're working on, listing the sample space, omega, can be quite tedious. It's good to have a plan as far as like how you're going to organize your thoughts. So if I was going to list all the things that can happen when I flip 4 coins or 1 coin 4 times, I'm going to start by doing it by the number of either heads or tails. So I could get 4 heads. There's only one way of doing that. I flip a head, then a head, then a head, then a head. Or I could get 3 heads. Well, I could either get head, 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 tail, or head, head, tail, head. I'm just moving the tail to the left. So head, tail, head, head, or tail, head, head, head. Those are all the ways I could get 1 tail and 3 heads. If I wanted to get 2 heads, this is the one that's the hardest to kind of list out. So I'm going to start by putting as many heads. I'm going to start off with, I think, heads, heads, tails, tails. And then I'm going to let one of these heads move to the right step by step. So the next one's going to be heads, tails, heads, tails, and then heads, tails, tails, heads. That head has moved as far to the right as possible. So now I'm going to shift this head over 1 and this head back as far as I need to. So the next one's going to be tails, heads, heads, tails. And I kind of repeat the process. Let this one head move over, tails, head, tails, heads. It's at the end. So I shift this one over. And the last one is tails, tails, heads, heads. There are other ways of organizing your thoughts. That's just kind of how I think of it. I think of fixing things and then letting one of the things kind of move one by one by one until I've kind of exhausted all the possibilities. 1 head should be easy because it's the same as the 3 heads, just interchanging the heads and the tails. So I could write this 1 head as tails, 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 heads, or tails, tails, heads, tails, or tails, heads, tails, tails, or tails, tails. Sorry, or heads, tails, tails, tails. Said it was easy, and then I proceeded to make it not look easy. And finally, 0 heads. There's one way of getting that. So tails, 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 tails. By the way, this is a good example of how like 4 choose 0. The number of ways of choosing 0 things from 4 things is 1, because there's exactly 1 way of choosing 0 heads out of 4 coins. This way, where you get 4 tails. All right, so note, not surprising, I suppose, the number of elements in the sample space is 1 plus 4 plus 6 plus 4 plus 1, or more easily seen as 2 times 2 times 2 times 2. Each coin flip, there are 2 possibilities. And so you have 2 for the first coin, 2 for the second coin, 2 for the third, 2 for the fourth, and you multiply all this together and you get 16. Another way you could see that if you really want to, you kind of make a branching tree. Like you could say at the first branch, you get heads or tails. And the second branch, heads or tails. Heads or tails. The next branch, all these heads, tails. And the final branch, oh look, there's 16 paths. And each path corresponds to exactly one of the things I've written over here. Heads, 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 tails, heads, tails, tails, heads, and so on and so on. Kind of a neat way of looking at it, actually, I think. But the real point here is that you don't have to draw that diagram or do all this to know how many outcomes are possible. We know that each coin has 2 possible outcomes, and so we multiply those 2 times 2 times 2 times 2 together and get 16. I should also mention that each of these here, the number of ways of getting 4 heads or 3 heads or 2 heads or 1 head or 0 heads is exactly 4 choose 4, 4 choose 3, 4 choose 2, 4 choose 1, and 4 choose 0. 4 choose 0 is 1, 4 choose 1 is 4, 4 choose 4 is 1, 4 choose 3 is 4, and 4 choose 2 is 4 factorial over 2 factorial times 2 factorial, which is exactly 6. It's kind of neat. So then we want to find some probabilities of things. And it's going to feel, I think, relatively straightforward. If I can move the page. For example, I could ask, I should be specific here. So I just like to say, like, what's the probability of a thing happening? But really, we should use the language that's appropriate here. We should say something like, let A be the event of flipping exactly 2 heads. What's the probability of event A occurring? So what's the probability of A? Well, it's exactly going to be the number of ways of getting event A to happen divided by the number of total things that can happen in your sample space. I don't think we need to write this, honestly. I would just say it's going to be number of ways of getting 2 heads, which is 6, over the total number of things that could happen, which is 16. And honestly, if I was doing this on my own, I would just write like something like probability of 2H for 2 heads, because that seems more normal than writing out A is this, and then probability of A. But here we go. I would reduce this fraction to 3/8. Probably not absolutely required, but worth doing. Okay, let's let B be the event of flipping, getting whatever, 3 heads or 4 heads. What's the probability of B? Well, how many ways can we get 3 heads? Everybody. How many ways can we get 4 heads? Right, so there's 5 ways we can get 3 heads or 4 heads. So the probability is going to be 5 out of 16. The number of ways of getting what we want divided by the number of ways of getting what can happen. You could have broken this up if you want to as the probability of 3 heads plus the probability of 4 heads, which is exactly 4/16 plus 1/16, which is 5/16. So again, just trying to really emphasize here the nature of the fact that the probability of something is just the number of ways of that thing occurring divided by the number of ways anything can happen in your sample space. And so one more. And let's just write it the normal way. What's the probability? Normal meaning like we don't need to come up with this. We don't need to give it a name. What's the probability? Can I spell? Maybe. Of flipping at least 1 head. So here's a couple ways we could write this. I would write this as the probability of the number of heads being bigger than 1, smaller than 1. If we want to be at least 1, if I'm between 0 and 1, then I am less than 1. If I want to be at least 1, it means I want to be like, if I want to be at least 35 years old, am I older than 35 or younger than 35? Older. If I say I want to be at least a certain number, it means I am that number or larger. So when I say I want at least 1 head, I want the number of heads to be greater than or equal to 1. If I said at most 3 heads, I would want the number of heads to be less than or equal to 3, because 3 should be the biggest value, the mostest value. So we're going to write this as the probability that the number of heads is equal to 1, plus the probability that the number of heads is equal to 2, plus the probability that the number of heads is equal to 3, plus the probability that the number of heads is equal to 4. which is going to equal, well, the probability that you get one head is 1 out of 16. Sorry, 4 out of 16, apologies. And 2 heads was 6 out of 16. And 3 heads was 4 out of 16. And 4 heads was 1 out of 16. For a grand total of 4 plus 6 plus 4 plus 1, which is 15 out of 16. Or we could do less work. We could use the complement. Or really, the better word here is the leftovers, right? The complement is just the leftovers, all the things we didn't use. So the complement, instead of being bigger than or equal to 1, we want to be everything else, which is strictly less than 1. So the complement here is that the probability of the number of is that the number of heads is strictly less than 1. There's only one option there. If I have to have less than 1 head, that means I can have how many heads? Right, that's the only number left, right? 0. So this is the same as writing the probability that the number of heads is equal to 0. Okay, well, we can calculate that. That's equal to 1 over 16. But now here's the idea. We know, or at least I'm going to say, and then you're going to know, that the probability of all the things happening should add up to 1 or 100%. So the probability of having 0 heads plus the probability of having the number of heads being greater than or equal to 1, that's everything, right? You either have 0 head or 1 head or more than 1 head. Those are the only possibilities, and all those possibilities should add up to 100% or 1.00 as a decimal. But if we know that the probability of 0 heads is 1/16, then we can find the probability of being greater than or equal to 1 head is going to be exactly 1 minus 1/16, which is 15/16. And that is often the way we calculate something like this, where they ask you to find the probability like something is bigger than or equal to 1 or 2, and it's like a bunch of stuff you'd have to add together. Instead, you say, oh, let's just find the complement probability and subtract that from 1. It's usually what people, it's a very common thing you get asked to do. All right, if you have questions, you can ask them. I'll go to the people on Zoom as well. If you have questions, I have the chat up. I can see it. So feel free to ask questions if you have them. All right, let's do another example, and then after that, I think we'll move on to talking about conditional probability. So I feel like I saw some people doing some set notation stuff. I think that was, yeah, right? There's some, no, maybe I did see that. Maybe it was for another class. Anyway, something you should see at some point. So let's say we have a 3. Sorry, my numbering is, I'm never good at the numbering. This is 2. I don't know why I'm writing a 3 here. Let's say we have a fair die. How many sides does dice have? Die? Right. It's a 6-sided die unless someone says it's something else. A fair die, it's 6-sided. And let's say that A is the event that an even number is rolled. And B is the event that a multiple of 3 is rolled. So let's actually write down what A consists of. A is going to be the set containing either rolling a 2, a 4, or a 6. Whereas B is going to be the event of rolling either a 3 or a 6. Those are the multiples of 3. Those are the even numbers. Let's illustrate this with a Venn diagram. I assume named after someone whose name was Venn. I have no idea where the name actually comes from, but I think everybody knows what I mean when I say a Venn diagram, right? Like the 2 circles or more that are overlapping. Cool. Everyone's good with a Venn diagram. So the big square here is like your entire sample space. And then our circles are A and B, and there's probably some overlap. In fact, let me ask all of you, what is in the overlap of A and B? 6, cool. There's 6 right there. And then in A, but not in B, are 2 and 4. And in B, but not in A, is 3. And then not in either of them are 1 and 5. Each event here has an equal probability. Probability of rolling a 1 is 1/6. Probability of rolling a 2 is 1/6. Each die roll has an equal chance of being rolled, which is 1/6. So let's ask some questions here. What's the probability of event A happening? Well, it's not a mystery, I don't think. There are 3 ways to get event A to happen out of 6 total things that can happen. The probability is going to be exactly 3 out of 6, which is 1/2. Similarly, what's the probability of B? Write it down. I know you know what the answer is. Let's see, B consists of rolling a 3 or a 6, so there's 2 ways of getting that out of 6 total things, which reduces to 1/3. Again, the number of ways of getting what we want divided by the total number of things that can happen. You could also think of this as the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6, which is 1/6 plus 1/6 plus 1/6. You could think of this as the probability of rolling a 3 plus the probability of rolling a 6, which is 1/6 plus 1/6, which is 2/6, which is 1/3. But I think you should try not to think too much about these things if you can get away with it. Like, not that you shouldn't think about them, but like if there's a simpler way to imagine what's happening, that is often useful. And not just because it's easy, but because it really makes it make more sense. And let's look at the next one, which is the probability of A intersect B. So intersection, or the overlap is what I often say, is where A and B have overlap. So what's the only element in the intersection of A and B? Right. So the probability of A intersect B is the probability of rolling a 6. And there's only one way to roll a 6, so that's a 1 out of 6 chance. Or probability. People often use the word and. I want A to happen and B to happen. The only way that both A and B can happen in one shot is if I roll a 6. I rolled an even number and I rolled a multiple of 3. Any other outcome is not in the intersection because both events aren't happening there. At least one of them is happening. So A and B. Whereas that's an intersection, but I like to say and. The probability of A union B, union, good name for it because it looks like a U, is the probability of being either in A or in B. 4 out of 6. 1, 2, 3, 4 ways of being in either A or B or both. Now, which reduces to 2/3. So often for a union, we think of it as an or. I should be very, very specific here. We mean a math or. A mathematical or is an inclusive or. So if someone was speaking to you in English and they asked you if you wanted soup or salad, you would say you wanted one of those things. You wouldn't say both, right? Even though, right, technically you could, but at a restaurant, that's called an exclusive or, meaning you get one or the other, but not both. And that is not the general meaning of mathematics. In math, if someone says the word or, they mean you can pick from column A, from column B, or one from both, right? You can, right? It's okay to have both things happening. That satisfies the or. So if I said, you want soup or salad in math language, you could say, well, I want soup and salad. That qualifies. So here, what that means, if I'm trying to find the probability of A or B, I can be in A or in B or in both. And I have to count all those things. And here's how we do it formulaically. if I didn't actually have this Venn diagram here, if I just knew the probabilities, here's what I say. I want to calculate the probability of A plus the probability of B. But if you just do that, you've overcounted. Because I've counted these three things, that's 3/6, plus these two things, and that's 2/6, but I've double counted the thing in the overlap. Since I've double counted that overlap, I'm going to subtract it off once to undo the double counting. Well, let's see if it works. Probability of A is 1/2. Probability of B, I should be smart and write it as 3/6, but I didn't. Probability of B is 1/3, and the probability of A intersect B is 1/6. 1/2 is 3/6 plus 1/3, which is 2/6. So that's 3/6 plus 2/6 minus 1/6, which is 5 minus 1, which is 4/6. Exactly what we got right there. So that's the formula for the probability of A union B. It's the probability of A plus the probability of B minus the probability of the intersection to undo the double counting of the intersection. Cool. All right. Yeah, we should start. Yeah, let's go there. We'll start. Yeah, start there, and then we can build into that. So we're gonna move towards some condition. Oh, yeah. What? One more time. So you can either see the 4/6 from just saying all the things in A or B. There's 4 things in there out of 6 total. Or you can say it's the probability of A, which is 3/6, plus the probability of B, which is 2/6, which gives you 5/6. But then you have to subtract off the probability of the intersection, which is 1/6. And it's a terrible word for me. 3/6 plus 2/6 minus 1/6 is 5 minus 1, which is 4/6. That's where that's coming from. But we're just really showing you the same if you do it either way. So if someone didn't give you this picture, all this information, and they just said if they just gave you, like, for example, if someone just told you this and this and this, then you could calculate this by using this formula instead of having this picture. Cool. All right, let's talk about some cards, and we'll build up to some conditional probability here. This is probably number 3, I think. I don't know. Why can't they write? Yeah. Cool, great. I mean, it doesn't really matter, but it kind of matters. So a card is chosen from a standard deck of how many cards? Right. Find the following probabilities. Find the probability that the card is, question A, an ace or a face. Okay. How many aces are there? How many face cards are there? What are the face cards? Right. So there's 3 different types of face cards, and there's 4 of each type. There's 12 face cards. So if we call being an ace event A and being a face card event B, then the probability of A union B is the probability of A plus the probability of B minus the probability of the overlap or the intersection. Yeah, sorry, question. Joker's not in play. There is no Joker. It's unfortunate that Joker and Jack both start with J, but when you see a J, if someone writes a J, they mean a Jack, not a Joker. Good question. That would be an interesting way to make it more complicated. So what's the probability of getting an ace? 4 out of 52. How about getting a face card? How about getting a card that's an ace and a face card? What card is that? What's the number I'm really looking for? how many cards are there that are both a face card and an ace at the same time? You drew a card and you saw an ace that was also a face card. 0. There are 0 such cards. Or in other words, the intersection of these two events is disjoint. There is no intersection there. So here we can just say the probability of A union B is 4 over 52 plus 12 over 52, which is 16 over 52, which I'm sure we could reduce to, I don't know, 4 over 13, I think. Okay. Yeah. Another word for being disjoint is mutually exclusive. So if two events are mutually exclusive, there's 0 overlap, or their overlap is empty. Okay, let's look at a more interesting question. How about a card that is a heart or a queen? We could list them all out. How many hearts are there? There's more than 4. So what's that? The ranks are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, and king. And for each rank, there are 4 of each rank. Right. For each suit, and the suits are hearts, diamonds, clubs, spades, there are 13 of each suit. Ace of spades, 2 of spades, 3 of spades, 4 of spades, 5, all the way to king of spades. So if I want to know how many hearts there are, well, there are 13 of them. How many queens are there? Right. No, well, I didn't say how many queens are there that aren't hearts. I just said how many queens are there. Right. So the probability of A union B here, getting a heart or a queen, is the probability of A, which you all just told me was there's 13 ways of getting a heart out of 52, plus the probability of B, which is the probability of getting a queen, which is 4 out of 52. But then, as Maggie so keenly observed, there is a card that is in the overlap, the Queen of Hearts. And that overlap we've double counted. We counted the Queen of Hearts here in these 13 hearts, and we counted the Queen of Hearts here in these 4 queens. So we have to subtract off the probability of the intersection, which is 1 out of 52. Is this the most straightforward way of doing this? Probably not. You could probably more easily just count up the cards you were interested in. You can say, well, there's 13 hearts, and there's 3 more queens that aren't hearts. Oh, I got 13 plus 3, which is 16, which is exactly what I'm getting here. 17 minus 1, 16 out of 52. Which is coincidentally the same probability as the previous question, but not for any good reason. It's just a coincidence. Okay, this one's going to feel kind of silly. How about the probability of getting a red card or a black card? Now, if we were trying to do as little work as possible, the probability is 100%, right? 1. There's a 100% chance or a 1 probability that you're going to get a red card or a black card. That's the probability of getting a red card plus the probability of getting a black card minus the probability of getting a card that is red and black. There are no such cards, just like there weren't any ace cards that were also face cards. But the probability of getting a red card is 26 out of 52. Probability of getting a black card is also 26 out of 52. And so you exactly get 1. 100% of the time, you will get a card that is either red or black. Okay. Let's look at a little bit of poker stuff. So let's say we have 5 cards. Although you can have poker games that have more than 5 cards in them, we still talk about playing 5-card hands because that's the standard way of doing it. So 5 cards are dealt from a deck of 52. I really should just not even say that. 5 cards are dealt. And unless someone says you have something weird, like a couple extra jokers in the deck, we're assuming, which no, people play with jokers, that's a thing. We're assuming that there are 52 cards in the deck, unless someone says something else. So what's the probability that all 5 cards are hearts? Or in other words, what's the probability of getting a heart flush? Okay, well, how many ways could I get 5 hearts? How many hearts are there? How many different ways could I choose 5 of those cards from those 13 cards? Right, exactly. So the number of ways of getting 5 hearts is 13 choose 5. Divided by the number of ways of getting any 5 cards. Well, how many ways can you choose 5 from the entire deck? Right. You're going to see a lot of 52 choose 5 when you talk about probability of poker hands. And you should not do any more work here. You should not write this out as 13 factorial over 8 factorial times 5 factorial over 52 factorial over 5, right? No, none of that. You leave your answer like this. Okay, here's a slightly different question. What's the probability of getting any flush? Meaning it doesn't have to be a flush with hearts, it can be a flush with spades, or a flush with diamonds, or a flush with clubs. It's actually both simpler and more complicated than that. So we just found the number of ways of getting 5 hearts. How many ways would there be of getting 5 spades? In fact, let's do it this way. Let's do it as hearts plus spades plus diamonds plus clubs. So how many ways can I get a heart flush? Right, 13 choose 5. How many ways can I get a spade flush? How many ways can I get a diamond flush? Right, and then a club flush. All of that divided by 52 choose 5. Or more easily written, 4 choose 1, the number of ways of picking a suit. There's 4 suits to pick from. I'm going to choose one of them times 13 choose 5 divided by 52 choose 5. So I took my previous answer and essentially multiplied it by 4, because for every way I can get a heart flush, I could also get a club flush in the exact same way, or a diamond flush in the exact same way, or a spade flush in the exact same way. But really the idea here is you're first choosing the suit, and then once you've chosen the suit, you're choosing 5 cards from that suit. Kind of cool. Yeah. Let's do one more. Let's say this would be a kind of a disappointing hand. What if you had exactly 4 hearts? Okay. So how many ways can we choose 4 hearts? 13 choose 4. Okay, but it's a 5-card hand. So the other card that isn't a heart has to be something. How many choices do I have for that card? Not all 52. I don't want to pick another heart. 52 minus more than 4. Because I'm not just excluding these 4 hearts I picked. I also don't want any of the other hearts I didn't pick. 52 minus 13. Because there's 39 other cards in the deck that aren't hearts. And from those 39 cards, we're going to pick one of them. I suppose if you prefer, and I'll say this in a second, actually, I'll just say it in a second. Divided by 52, choose 5. If you prefer, though, you could have seen this as 13 choose 4 times pick a suit. How many suits are left to pick from? How many suits am I picking? And then from the suit you picked, how many cards are there? No, how many cards are there? Let's say we picked spades. How many spades are left in the deck? Right, we didn't use any of them. There's 13 left. And how many of them do we want? Just 1. And that number there, 3 choose 1 is 3, 13 choose 1 is 13, 3 times 13 is 39. Just like over here, 39 choose 1 is 39. So you can often break down these card problems into deciding on suit and rank in whatever order makes sense to do it in. Not always, but a lot of the time. Divided by 52, choose 5. Okay, so now here's the kind of extended question that's going to kind of be the same as before. How many ways can you get exactly 4 of one suit? Exactly 4 of any suit. Well, let me ask you all, what do you think I could do to my previous answer to get my new answer? Exactly, multiply it by 4. I'm going to say 4, choose 1. First, you're picking the suit instead of just deciding on hearts, and then the rest is the same. So it's going to be 4 times as many possibilities. 4, choose 1, times 13, choose 4, times 3, choose 1, times 13, choose 1, over 52, choose 5. We picked our suit. We picked 4 of those cards. We picked our other suit. We picked 1 of those cards. Neat. Sorry, I've been not quite getting to conditional probability quite yet. So let's move that way. So let's say we draw 2 cards from a deck, or just 2 cards from a deck of 52 cards. So we draw 2 cards, and we want to find the probability that the first card is a heart and the second card is a heart. And we're going to break this up into 2 different ways of thinking about it. So the first iteration is going to be if we replace it. So if the first card is replaced back into the deck after it's drawn, or I should say before the second card is drawn. Okay, well, let's say that A is the event that the first card, bless you, is a heart. B is the event that the second card is a heart. So I want to find the probability that A and B happen, right? The first card is a heart and the second card is a heart. That's the intersection. And in this case, we can say it's going to be equal to the probability of A times the probability of B. The probability of the first card is a heart is what? What's the probability of drawing a heart from the top of the deck? All right, how many hearts are there? 13. How many cards are we drawing from? 52. And then if we put that card back in the deck, it's like it never happened. What's the probability that the second card is a heart if the deck is still full? Right. It's again 13 out of 52. Okay. And you could simplify this if you wanted to. It's 1/4 times 1/4, which is 1/16. But now here's where it gets more interesting. What if the first card is not replaced? Well, now something different is going to happen. The probability of A and B is going to be the probability of A, which is still 13 out of 52. But now, knowing that the first card was a heart affects the probability of B happening. If you remove 1 heart from the deck, what's the probability that the next card you draw is still going to be a heart? Well, how many hearts are left? Out of how many cards are left? Right. So we're going to have to multiply by not the probability of B, but the probability of B given that A has already happened. The conditional probability. And that's exactly going to be 12 out of 51. Sometimes it's really easy to talk out to yourself what the conditional probability means. Like you're like, oh, this thing already happened. That means I have a reduced sample space now, and I'm asking what the probability is of this event in this new reduced sample space. And sometimes it's much more formulaic. I usually try to tend towards the first way, but sometimes you have to go with the second way. So here we're going to get 13 out of 52 times 12 out of 51. Again, we don't really care what the numbers are, but I guess we care kind of. That's going to be 1/4 times both 12 and 51 are divisible by 3. That's going to be 4/17. So we get 1/17. A notably different probability. So this equation right here gives rise to the conditional probability equation. And there's many versions of it. I'm going to show you the one that I think is the best one to remember, and then we can talk about other versions of it. So here is my personal favorite version of the conditional probability formula. It's that the probability of, what have we got here? Yeah, I'll try it this way. Of B given A is equal to the probability of A intersect B divided by the probability of A. Which I'm really just taking this formula that I've circled in red and dividing both sides by the probability of A. Like the probability of A intersect B divided by the probability of A equal to the probability of B given A. That's my favorite way because I feel like it's the way that makes the most sense. You're essentially saying A has already happened. So in your Venn diagram, where there's A and there's B, you're already living in the land of A. So we're kind of completely stuck in the circle of A. And then you're saying, great, given that we're living in this new smaller sample space, what's the probability of B happening? Well, the probability of B happening, B only lives over here, which is the intersection of A and B. So it's exactly the intersection of A and B divided by the A part, which in my picture are red and green. Hopefully you can kind of see the red and the green. Kind of. Okay. That's the whole idea, right? You're just saying, okay, we know A has happened. So then the probability of B knowing that it has happened is the ways you get B out of the ways that you are allowed to get it. And then you can also write this formula in the flipped way. You can write it as the probability of A given B equal to the probability of A intersect B divided by the probability of B. And finally, my least favorite version of the formula, but it is useful. The probability of A intersect B is equal to either probability of A given B times the probability of B, or probability of B given A times the probability of A. Right, if you want A and B to happen, then you have to say, well, it's the probability of B, and you have to multiply by the probability of A, knowing that B has already happened. Or it's the probability of A, and you have to multiply by the probability of B, knowing that A has already happened. Cool. So, time. Let's look at this one example, and then we'll call it a day. So, yeah, we'll do that. And you need to try and leave early here, but let's see. So let's see this example here. We've got one card drawn from a deck of 52. And I want to know the following. Yeah. Excuse me. I want to know. Sorry, I'm trying to. Yeah, okay, that's fine. Yeah. Find the probability that the card is a queen. We'll call that event A, although I would probably call it event Q, given that it is a face. So that would be Jack, Queen, or King. We'll call that event B. Okay, in my mind, here's the easy way to do this. We're going to use the reduced sample space. So knowing that B has happened, that I either have drawn the jack, queen, or king, how many ways does that happen? How many jack, queens, and kings are there in total? There's a few more. 4 times 3, which is 12. So there are 12 things to choose from. That's my total space. Okay. How many ways do I get what I want? What's the probability of getting a queen from these 12 cards? Well, how many queens are there? Right. So it's the 4 in 12 chance of getting a queen. If I know that one of the cards, if I said, I know you drew a face card, but I'm hiding it from you. What's the probability that it was a queen? Oh, it's a 1/3 probability. Or we can use the formula and say, okay, I want to know what's the probability of getting a queen given that it was a face card. So that's going to be the probability of A and B divided by the probability of B. In this case, A and B being a queen and being a face card means it's a queen. Sometimes the overlap is just all of the smaller space. Not always. The probability of being a queen is 4 out of 52. The probability of getting a face card is 12 out of 52. And this exactly reduces down to 4 out of 12, which is 1/3. These feel not too different from each other, but sometimes it feels really a lot easier to be like, okay, my new space is just a smaller thing, and then what's the likelihood or how many ways can I get what I want out of that new space? Right. Whereas in general, if I just said what's the probability of getting a queen, probability of getting a queen would be 4 out of 52, which is 1 out of 13, which is very different than the probability of getting a queen knowing that the card is a fixed card. All right, I should stop there because I have to be available for a phone call at 2 p.m. So I'm going to stop there a little bit early, and I'll see you all on Friday.